All righty. Can you all hear me? Good? All right, thank you, and I really appreciate everybody waiting. We got our extra guests here, so we're super excited to have you here. I just want to start by saying that 2024 is a very special year up here at Mount Wilson and at Carnegie Observatories. We're celebrating the anniversary of the discovery of the universe by Edwin Hubble, right here with the telescopes you're going to look at today. Yes, Edwin Hubble does it so. So when Dan asked me to give a talk, I thought, well, why don't I give a talk about how the universe looks today, our kind of modern version of Hubble's universe, so to speak. But because we are at Mount Wilson, I have to do at least a little bit of history because it would be wrong. I know many of you probably have not been here before, so you really should understand just how special this place is. So what do I mean that Edwin Hubble discovered the universe? Well, prior to the result that I'm going to talk about that happened in 1924, astronomers were not sure if the universe was a single collection of stars called the Milky Way galaxy, which we live in, or if there were other systems like the Milky Way out there. And what Hubble showed in 1924 was that there were, in fact, other galaxies out there. And in fact, this image, this is a deep image from the James Webb Space Telescope. It may not look terribly impressive, but every little thing you see on there is a separate galaxy. These are many, many Milky Ways, effectively, you're seeing, and there's probably close to 10,000 in this single image, which is a tiny little speck on the sky. And I'll talk about that in a bit. So Edwin Hubble was the one responsible for showing that those systems existed. But he was not the first person to think that there might be something beyond the Milky Way. That goes all the way back to 1750 with a man named Thomas Wright, who was the first person to explain why the Milky Way appears to wrap around us. If you go and watch the Milky Way from any site, you see it kind of wraps around the sky. And his idea was if you had a disk of stars and you were in that disk, you would see it kind of wrap around you. But he also went on to, and the reason I mention him here is because he went on to show that he postulated that maybe there were other systems like the Milky Way out there. And these things became known as island universes in the 1700s. And the actual first time astronomers realized there was something with a spiral structure, they were called spiral nebulae, we now call them spiral galaxies, was this beautiful drawing. This was the first drawing of such a thing made with this incredible telescope by William Parsons. He built this telescope in his backyard in Ireland, which is probably not a great place to do astronomy given the weather in Ireland, but that's a pretty remarkable discovery. You could see his drawing of the galaxy, and there's a current image of that from the Hubble Space Telescope. He did a really great job. So this was the first time we discovered what were known as spiral nebulae. And you might have looked at that nebula and went, well, that looks like a galaxy. That's probably what the Milky Way looks like. So why didn't that idea catch on? And it didn't catch on because the most prominent astronomers of the 18th and 19th century didn't like that idea. They thought that all the fuzzy things on the sky that we call nebula must all be the same sort of thing. And their idea was that these things were probably places where new stars were forming. And so you see these four examples here. Those are four things that astronomers would have referred to as nebulae back in the time, but they are very different phenomena. The furthest one on the left there is the Orion Nebula. That is a star-forming region, which is in fact forming stars. The one to the right of that is called the Ring Nebula, and I think you'll probably get to see the Ring Nebula tonight through the 100-inch. That is basically the death of a star like the sun, where the outer layers kind of puff off and extend into space. Right next to that is the death of a massive star, and these are these massive explosions we call supernovae. And then on the right there is a spiral nebula. So the astronomers at the time looked at these four things and said they must all be the same. And so these aren't island universes. They must be star-forming regions. That changed in the 1910s when Curtis, a famous astronomer at Santa Cruz, made a really brilliant observation. He saw that there were some of these cases where these things were edge-on. And if you look at that edge-on image, you see the dark lane running across it. And he compared that to the dark lanes one sees from the Milky Way. Now, you probably don't see the Milky Way like this. You certainly can't see it like this in Southern California. But if you go to Chile, you do see it like that. And you see all that dark stuff. That dark stuff is dust. And so he looked at these edge-on things and said, these must be Milky Ways. So that was he became the person pushing for the island universes. Now, quite ironically, right up here was the most famous astronomer probably at the time in Southern California, a man named Harlow Shapley, who used the 60-inch telescope here, which is the other telescope you're going to get to see. That is an incredibly, remarkably historic telescope, because that was the telescope that was used for the first time to measure the size of the Milky Way. And Shapley got a number that was so huge in his mind, 300,000 light years across, that he said, how could there be anything bigger than that? That had to be the whole universe. He did one other really important thing that I think is interesting when you go look at that telescope tonight. Not only did he measure the size of the Milky Way, he was the first person to show that we're not at the center of the Milky Way. In 1918, prior to 1918, humans thought the solar system was at the center of our galaxy. And on that telescope right up the hill there you're going to see, he showed that we're about 2/3 out. So when you see those t-shirts, some of you probably have them because this is a room of, I'm guessing, science geeks. If you have one of those shirts that says you are here, where they're 2/3 out, that is Harlow Shapley, and it happened right up here on our hill. But Shapley, because his Milky Way was so big, he said there can't be anything more than that. This led to one of the most famous incidents in astronomy. It was called the Great Debate, where Shapley, who said the universe was the Milky Way, and Curtis, who said there were lots of Milky Ways, were supposed to debate and decide who was right. Because this was the question of the day in 1920. Now, unfortunately, it wasn't much of a debate because Shapley refused to talk about, he just talked about the size of the Milky Way. He refused to talk about the spiral nebulae, and Curtis just did his talk. So it wasn't really a debate, but this tells you this was really the important question of the time. The man to answer the question was, of course, Edwin Hubble. He arrived here in Southern California in 1919. He had been working at Yerkes Observatory out in Wisconsin. And here at Mount Wilson, he had access to the biggest telescope in the world. And there's the beautiful image of this telescope. And this is the telescope you're going to get to look through tonight. This is the Mount Wilson 100-inch telescope. And this telescope came online here in 1917, but it always takes us a year or two to get them going. So by the time Hubble arrived in 1919, the telescope was really ready to be used. And with its large aperture, this was the biggest telescope in the world by a lot at that point, it was able to see individual stars in these nearby spiral nebulae. No one could do that before. And so Hubble decided he was going to look at these nebulae and look for individual stars. He was particularly interested in a type of star called a nova. You may have been hearing a lot about a nova because there's one that's supposed to get bright in the next few months. It's in the news all the time if you're reading science news. A nova is a star system with two stars orbiting each other. One is a white dwarf, which is the remnant of a star like the sun. And material from the bigger star actually falls on the white dwarf, and the white dwarf gets very bright temporarily, and then it'll fade for tens or hundreds of years. These are called nova. So that's what Hubble was looking for in 1923 originally, sorry. This is one of the first images he used of the Andromeda galaxy, taken with the 100-inch telescope you're going to use. And the next night he observed it again because he was looking for these stars that suddenly got bright. And what he saw was you see these three little ends there, he wrote. Those were objects he identified as nova. So he thought he had found 3 of them in this particular spiral system, which we call Andromeda. So many of you will be familiar with that. But Hubble was smart, and he went back and looked at earlier plates he had taken, and he realized quickly that one of those stars didn't get bright and then fade. It got bright, faded, and got bright again, which is not what these things should do, at least over very short time periods. So this meant this was not a nova. This is what we call a variable star. It in fact does this at a very regular cadence. And certain types of variable stars are very interesting because they allow us to determine distances in astronomy. The most famous kind, which is the one he found here, was what we call a Cepheid variable. And the reason is because the time it takes for it to go from its brightest to its faintest to its brightest, that amount of period that you can measure quite easily from watching it over many nights, tells you how much energy the star is giving off. And if you know how much energy a star is giving off, and you can see how bright it appears to be in the sky, you can work backwards and determine the distance. So these Cepheid stars are still used today as one of our primary distance measurements. What Hubble did was he wasn't sure this was that type of variable stars. There's lots of variable stars. So he kept observing here at Mount Wilson. And in February of 1924, he realized he had a Cepheid variable. And he measured the distance to Andromeda. And what he found was that it was very, very far away. He measured it to be about 1 million light years away. This meant it could no longer be in the Milky Way. He had, in fact, shown that Andromeda was a separate system. And in fact, he took note, he didn't waste a lot of time to tell his nemesis at the time, who was Harlow Shapley. Remember, Shapley thought the universe was just the single Milky Way. And so you can read the quote there. You'll be interested to hear that I found a Cepheid variable in the Andromeda Nebula. And then he went on to tell Shapley that it was a million light years away. I love Shapley's response. So Shapley apparently got this letter, and one of his colleagues was in the office when he read it, and he goes, "Here is the letter that has destroyed my universe." And in fact, but this was in fact the discovery of the universe right here at Mount Wilson in 1924. Now Hubble didn't make the announcement about this until January 1st of 1925. And he took the data, I showed you that data he took in actually 1923. So here at Mount Wilson and down at Carnegie, we're celebrating a very long discovery of the universe, something like 15 months, with the actual discovery to the world happened on January 1st of 1925. And here's just some news clips from the time. Scientists sees new universe, another universe seen by astronomers. Hubble had indeed found the universe. In my mind, this is the most important astronomy result of the last 400 years. And let me tell you why I say that. What happened 400 years ago? Well, 400 years ago, Copernicus and Galileo put the sun at the center of the solar system. That was a revolutionary idea that no one anticipated. What Hubble did here was he basically discovered a universe. It was equally as revolutionary as Copernicus and Galileo's work. And once again, you're sitting right where it happened. So this is really remarkable. So thank you for letting me talk a little bit of history, because I was going to talk just about the modern stuff, which I'm getting to. But it's important you understand just how important this place is. Okay, Hubble went on for his second big discovery. Now, often if you read about Hubble, this is the one people think is most interesting. That's why I had to say the other one is more interesting. Is it more interesting to discover that the universe exists or that it's expanding? And they're both pretty impressive. In fact, this is probably the second most important result of the last 400 years. What Hubble did was he used these same Cepheid stars in other galaxies now, and he showed that the ones that were further away were moving away from us faster. And this is because the space is actually increasing between the galaxies, as a way to think about it. He never said, by the way, Hubble never said the universe was expanding. He didn't like making claims like that, but it was very clear that that's how it was interpreted by everybody else. This got a lot of attention for Hubble. Here's a picture taken from the Carnegie Observatories, our offices down on Santa Barbara Street in Pasadena. This was a day when Albert Einstein gave a talk, February 5th, 1931. And the reason the date is so important was because this is the time Einstein himself, down there in our headquarters at Carnegie Observatories, admitted that he had made a mistake. This is the so-called biggest blunder. When Einstein looked at his equations of the universe, he had assumed the universe was static, that is, that it did not change in size over time. And it was only after spending time with Edwin Hubble up here and down in Pasadena that he finally admitted, 2 years after Hubble had found this result, that in fact the universe was expanding and he made a mistake. So anyhow, two huge results. So now I want to follow up on where those results look like today. So I'm going to start by talking about galaxies. So Edwin Hubble showed that external galaxies exist, but we now know a lot about what these systems are. Now I want you to imagine you're sitting in the Milky Way right now, that's where you are, but you can zoom back out and look at yourself and look at our system. This is kind of what your home would look like. This is what a typical spiral galaxy like the Milky Way would look like. What you're seeing here in this visible light image is the light of the stars. The stars are the things that produce the light, and you're seeing the light of about 200 billion stars. That's a really big number. Let me put that in context again. The sun is one of 200 approximately billion stars in just the Milky Way. These are incredible systems. The other thing you can see a little bit here, and I already talked about, is you see the dark parts. The dark parts are gas and dust, primarily dust is what you're seeing. And that's also part of the galaxy, although it ends up being a much less significant component than the stars. And you can see the size of the Milky Way. It turns out to be about 100,000 light years across. It turns out that Shapley had the number wrong because he had the wrong relationship. He used the wrong type of star, but it's okay. He used the Cepheid, just the wrong Cepheids. And so this is the real size. It's just still a very incredible system. Now, although all we see with our eyes in an image like this is the stars, we know that there must be other things there. In particular, we know that there must be a lot of planets there. And I'd say the hottest field in astronomy over the last 20 years has been the discovery of planets around other stars. You're hearing this all the time on the news, a new planet being found. We call these exoplanets. That means planets outside of our solar system. And as of today, there are 5,690 exoplanets. You can go on the web and follow this day by day. That's a lot of planets. So we know of almost 6,000 planets around other stars. The reason I wanted to include this here, though, is these planets are really hard for us to detect, and we only can see them in what we would call the solar neighborhood. So you see there's a diagram, that's a drawing of what the Milky Way might look like, and you see the little circle with the sun. Almost all those planets are seen over that very little region. We cannot see exoplanets even over most of the Milky Way galaxy. This is a really challenging thing. But already we see 6,000 in just that little part of the Milky Way. And if you look on average, a star in the Milky Way in that little area has about 5 stars. So if you assume that that area that we're in is comparable to everywhere else in the universe, you can say every star in the Milky Way has about 5 planets. And if you do that, you get a number which is about 1 trillion planets. Now, these numbers are big and really hard to understand, but you can understand 1 trillion is a very big number. Once again, the Earth is one of 1 trillion planets in the Milky Way, just to give you an idea. Now, it turns out that the stars and the planets, of course, are really interesting. That's what the astronomers observe. But there's the component that we don't see directly, but we can detect, and this is due to another very famous Carnegie astronomer. She was, in fact, the first woman astronomer to use the telescopes here in Southern California, the Palomar telescopes that Dan mentioned earlier. Her name was Vera Rubin. She should have got a Nobel Prize. She's unfortunately no longer here, so she can't get it. She was working with a gentleman named Kent Ford, and what they were studying were these spiral galaxies. And what they were doing was measuring the speeds of stars in the galaxy as you go further and further out from the center. Now, in the solar system, the system we live in, the sun has most of the mass of the solar system. So most of the mass of the solar system is right at the middle. This means as you move away from the sun, things go slower because the gravity is stronger near the sun than it is further away. Now, if you look at a galaxy, I'll go back to this picture again here. If you look at this, there's a higher concentration of stars near the center of the Milky Way or a galaxy than as you go outward. So what you might naively expect is that the stars would move faster near the middle of the galaxy than in the outer parts. And that is not what Vera Rubin found. What they found, you see that green line is the observed data. What you expect is that there would be a peak, and then as you go out to the edges of the galaxies, the stars would move very slow. And so the fact that the velocities continue out as you go to the edges of the galaxy means that there must be a lot of mass as you go further out. So even though we don't see the stars die off, there's a lot of stuff beyond that we don't see. And this is in fact the dark matter. Now we still don't really know what the dark matter is. There's a lot of experiments going on. Most likely we think it's some sort of subatomic particle that we have yet to discover. But this is one of the biggest mysteries in astronomy today still. But what I will say is about 90% of the mass of a galaxy is in the dark matter. So the dark matter is the dominant component, even though we don't see it directly. So I've just added the dark matter on there. So we have 200 billion stars, 1 trillion planets. About 90% of the mass of the galaxy is in dark matter. We're not done yet, though. There's one other really interesting component that we've discovered in the last 20 to 30 years. And that is that every galaxy, at least every big galaxy, has at the very center a supermassive black hole. And that is a really interesting and important result that we still don't fully understand. So first of all, let me remind you what a black hole is. A black hole is a system that has such strong gravity that even light could not escape it. If you sit here on Earth and you hold a flashlight out in the middle of the night, the light goes up, you see it go up. That light, in theory, would escape the Earth because it's going at the speed of light. On a black hole, you couldn't do that because even the speed of light would not be enough and the light would bend back down onto the black hole. But a supermassive black hole means it's a black hole that's we find about 1 million to 1 billion times the mass of the sun. These are incredible monsters. And how do we know if we can't see the black hole? This is always a really good question. Well, the first evidence for black holes came from seeing the light around the black hole. As material swirls towards the black hole, it creates what we call an accretion disk. And in this disk, there's very high friction. You can do friction with your hands. I always do this with a kid. You don't need to. What it does is it warms that material up. And in the case of the black hole, the gravity is so strong that material emits huge amounts of energy. Sometimes visible light that we can see, but they shine very brightly also with X-rays. And so, even though you don't see the black hole itself, you can see right around the black hole this incredible light source. And these were discovered, once again, here in Southern California. In the 1960s, people finally realized this. The term quasar, you probably heard that term before. A quasar is just one of these black holes that's accreting a lot of material. And on the right, you can see an example. You can see how there's this very bright source. There's actually a galaxy there, but it's so hard to see because the center, the black hole, is dominating the energy. And so that's how we can find these black holes. We can see them actually eating material and shining. But there's another way, and this is one of my favorite results in all of astronomy, and this is by our colleagues Andrea Getz, who's at UCLA. This is a very zoomed-in version of our own Milky Way center. And we do this with the Keck telescopes in Hawaii. What you're watching here are individual stars moving in the center of the Milky Way galaxy. And what you'll see here is where there's the white star is where we think the center of the galaxy is. This is a time sequence, and you can see the year up there in the upper right corner, taken over like 30 years, I think, almost 30. So you watch the stars, but notice the stars. Notice what happens when they get near that white point. Especially there's that one on the yellow orbit there. We'll watch it again. You'll see how the objects speed up as they go towards that dark star. Well, that's because there's very, very strong gravity right at the center of that location. But there's not an object there. You don't see an object there. It's hard to tell because of the white star, but if you took the white star, trust me, it'd be black. And that's because we believe there's a black hole right there at the center. And so by using the velocities of these stars, we can estimate the mass of that black hole, and it's about 1 million solar masses. So this is, in fact, the black hole at the center of our own Milky Way galaxy. This is a very incredible result that won her the Nobel Prize back in 2020, for good reason. And of course, many of you have seen the first image of a black hole, which happened in 2019. And I have a little video to describe what you're seeing here. What you're really seeing is kind of the shadow of the black hole. You're not once again seeing the black hole itself, but you're seeing all the light around it. And this is a little video which kind of describes it. So light is coming from all different directions, and it's being bent around the black hole. But from our perspective, we're just seeing all the light that's bent into our line of sight, that is, that we can detect. And so that's what you're really seeing in this image of the black hole. Now you may know this was an incredible result. They'll probably get the Nobel Prize for this at some point. They haven't yet. But, and we now have done this with just 2 black holes. The one I just showed you was the first one, which is M87, which is a nearby very supermassive black hole. This is 1 billion times the mass of the sun. But they now have done this for the one at the center of the Milky Way as well. So we can even kind of take a picture of a black hole. Oh, I wanted to give you an idea of the scale of that. This is that image with the solar system. I don't know if you can see it. You see the orbit of Pluto. So these things are pretty big. They're the size of the solar system, but that's actually not that big compared to galaxies, but you can imagine all that mass in that little area. It's really incredible. Okay, so now you've learned all about galaxies. You know that they have about 200 billion stars, 1 trillion planets, they're 90% dark matter, and they have supermassive black holes. Hubble would be amazed by all of those things he would not have definitely known. I wanted to say that, but I've been showing you, what I've been showing you are spiral galaxies. I'm going to show you some other types of galaxies in a bit, but I wanted to also point out that galaxies come in different sizes, huge range of sizes, in fact. This is one of my favorite galaxies, the Sombrero galaxy. This has a disk, that's what you're seeing, the edge-on component, but it also has kind of a round component, which I'll talk about in a minute. So this is a very cool galaxy. I've worked on this myself quite a bit. And there's a little less cool looking galaxy in that little box there. But the incredible thing is that little dot is actually at the same exact distance as the Sombrero galaxy. So the difference you see in size is a real difference in size because they're at the same distance. And this little guy here is called what we call an ultra-compact dwarf galaxy. And that system has maybe 2,000 or 3,000 stars in it. So I just gave you a whole talk telling you a galaxy had 200 billion. That's the big galaxies like the Milky Way or like this Sombrero galaxy. But we actually see a whole range, including very, very small galaxies. And these are really interesting. Now you may ask a question. You're going to see, I believe, at the 60-inch, you might actually see what's called a globular cluster. Some of you may be familiar with that. These are in our own galaxy. These are systems of stars with thousands or even millions of stars. And this thing only has a couple thousand stars. How is this a galaxy and not a cluster, you might ask? The way we know that is because if you look at this system and study it, it has dark matter, and clusters do not. And so that's how we tell these small galaxies from small star clusters. There are different types of galaxies. I've been talking mostly about spirals, but the Sombrero I showed you is kind of a combination of a spiral and an elliptical. Elliptical is more like a football-shaped galaxy. You can think of it that way. And then on the right, you have these things called irregulars. These things just don't have any structure. Now, Hubble was one of the first person to really recognize all of these things. This would be considered his third big result. Although he doesn't get a lot of attention for this one anymore. But that was also work he did up here at Mount Wilson. What he did was he looked at the shapes of galaxies and came up with what we call Hubble's classification scheme here. And he basically came up with this is a tuning fork for galaxies, so to speak, where you have the ellipticals on the far left and the spirals. There are actually 2 different types of spirals, depending on whether they have what we call a bar. You can see that kind of flat structure in the middle on the lower ones. And for a long time, astronomers wondered, do the galaxies move in and out along this bar, along this system? And for the most part, they don't. But that doesn't mean that galaxies don't change. And that's the last topic I want to talk about, because this is one of my favorite topics. And that is, how do galaxies change in time? Well, one thing that can change a galaxy, we know, is a merger with another galaxy. And here's some spectacular examples. You're seeing galaxies that are interacting and merging. This one on the right was a new James Webb image that just came out a couple weeks ago. I think it's pretty spectacular. Well, what is happening? What happens when you take two galaxies and smash them together? So I have a little simulation. This is work done at Carnegie by one of our postdoctoral fellows. It's a pretty old result, but I was on this paper, so I'm including it. What you see here are two galaxies. You see they just passed each other. The other one went off, but he's going to come back. On the upper left there, you see the time in billions of years. So 1 is a billion years. So we've just passed almost, it'll be 2 billion years in a bit. Eventually, gravity is going to bring that second guy back down. He kind of got back to normal, you can see. But this time he's not going to get so lucky. And this time the two are going to merge. We were trying to explain a particular observation I took in Chile, and there's the observation. You can see the simulation did pretty good. Yeah. But the fun thing about the simulation is you can run it forward and see what happens. And you might guess what will happen. They will end up forming a single galaxy. And so this is what that system will look like in a couple more billion years. It will form a single galaxy. So in fact, you will experience, well, you won't experience it most likely, but your galaxy will experience it. Should be really careful. In about 5 billion years, the Milky Way and Andromeda will go through a similar merger process and become a single object. Like I said, we probably won't be here to see it, but it'll be pretty spectacular for when it happens. One of the remarkable things is I'm taking a galaxy, Andromeda, with say 200 billion stars, and I'm taking the Milky Way with 200 billion stars and smashing them together. And you would think a lot of interesting things would happen, right? Turns out, in a case like that, the 200 billion and 200 billion, if you were still here, if Earth was still orbiting the sun, we would continue to orbit the sun. We would just have a lot more stars in our sky. 200 billion and 200 billion, there's so much empty space between stars and galaxies that very little in actual real collisions happen between stars. So that's something to not worry about, even though we won't be here anyways. The other type of interaction that's really cool, and this is another thing I studied, so I threw it in, is galaxies can also interact with big gas clouds, and that can impact them. Galaxies like to occur together in space. You may not know this, but you live in what we call a group of galaxies. It's called the local group because it's local to us. And that's a small collection of galaxies, includes Andromeda, the Large and Small Magellanic Cloud, and a few others. But there are very big collections of galaxies that have thousands of galaxies that are all orbiting kind of a similar common mass there. And that's what you see on the left. All those galaxies are part of a single system, and we call these clusters of galaxies. These systems are so massive that they draw in gas from the intergalactic medium, and this gas, because there's so much gravity, heats up to very high temperatures, and they glow in the X-ray. So what you see there on the left and the right is the same part of the sky, on the left with the Hubble Space Telescope, and on the right with the Chandra X-ray Space Telescope. And what you're seeing on the right is basically the hot gas glowing. But as galaxies interact with that gas, that can also impact them. So here's another little simulation that shows it. This is a galaxy, this is a disk of gas in a galaxy. And imagine this galaxy is falling towards that pink hot gas. And so over time, what you see happens is the galaxy is going to be stripped of its gas by the interaction with the hot gas and form these beautiful tails. I'm going to show you some of these in a minute, real data. And so over time, what will happen is a galaxy which had a lot of gas and dust can be stripped entirely of its gas and dust because it's interacted with this hot medium. And why is that important? Well, without gas and dust, you can't form new stars. So effectively, this kills off a galaxy and it dies. But it's awfully pretty on the way. So we call these things jellyfish galaxies. Here's two examples here. And you see the spectacular tails there. You can see that basically the gas that's been stripped off both of these galaxies. So one of them is headed this way and the other one's obviously going the other direction. But anyhow, very spectacular examples. But the real way we learn about how galaxies have changed in time is by taking deep images with the telescopes that we have in space. And the first of these is named after Edwin Hubble because of his two big results. This is, of course, the Hubble Space Telescope. And this is my all-time favorite image in astronomy. I cannot give a talk without showing this image on the left there. This is called the Hubble Ultra Deep Field. What we did is we pointed the Hubble Space Telescope at a blank region on the sky and integrated away for 23 days. 23 days, it's a long time. And when you look at that blank region of sky and you add up all the light, you start seeing very, very faint things. And what you see in that image, everything you see in that image, is pretty much a galaxy. And that image alone has about 3,000 galaxies. Now you may be asking, how big is that on the sky? If you took a grain of sand and held it, pinched it and put it at arm's length, it'd be smaller than that. This is the tiniest little region on the sky with 3,000 galaxies. Now why are they so small? Some of them are really small. They're small because they're far away. And what this is important because this allows us to actually see what things look like in the past, because we are effectively seeing them in the past. So let me explain that. It takes time for light to come from distant parts of the universe, so by the time we detect it with our telescopes, we're seeing that light that left before. The common example I give is the sun is 8 light minutes away from the Earth. That means the light you see from the sun left 8 minutes ago. You are seeing the sun actually in the past, you just didn't know it. In this image, you're seeing objects that are very far away, so it's taken a long time for that light to reach us. On average, in that image, things are about 10 billion light years away. So you're seeing an image of the universe 10 billion years ago. Let that sink in. The Earth is less than 5 billion years old. This is an image of our universe 5 billion years before the Earth even existed. That's super interesting for astronomers, because what this means is, as an astronomer, I can look at how galaxies looked in the past. I can look at those modern examples, the ones I showed you, the bigger examples that are nearby, and say how have they changed in time. And so this is a super exciting field. Here, by the way, this took Hubble Space Telescope almost 30 years to get an image of this depth. There's an object in there, that little blippy thing, which is 13.4 billion years in the past. But it didn't take long for Hubble to become old news, so to speak, with the launch of the James Webb Space Telescope. This is the first image the James Webb Space Telescope took. It's a different field than the one I just showed you, but this image is already deeper than that one in 11 hours. Remember, I took 23 days to get that Hubble image. This is because James Webb is a much bigger telescope. It allows us to go much, much deeper. This shows it really well. This is the same field now. You see the Hubble image, you see the James Webb. You can see how much more detail you can see in James Webb. I often do the blink too. There's the Hubble, there's James Webb. One thing you'll notice, there's just a lot more galaxies that you can see in the James Webb data. Hubble, there's James Webb. It's really incredible. And James Webb is now taking many, many deep images. These are just some spectacular ones I picked out. I mean, there's so many of these right now. And I think I said this at the bottom here. In the last year, as we take deeper and deeper images of James Webb, we found the most distant galaxy 9 times. The record's been broken. It will continue to be broken for probably the next 10 years. So you'll read in the paper every month or 2 months, the most distant object found was James Webb. It's an incredible telescope. And this is currently the most distant thing we know about in the universe. It's just the red part of that little thing there. This thing is seen about more than 13.5 billion years in the past. Now the universe is 13.8 billion years ago was the Big Bang. So we're getting to the point where we are seeing these systems in formation. There's not going to be a lot more time, because at some point you get back to the Big Bang. By the way, we won't see the Big Bang because it took a while for the galaxies to form, but this is still incredible. We are seeing, this one's only 290 million years after the Big Bang. So some of the things we've learned from James Webb already in 2 years is, one, you can see already from the images I showed you, we're seeing many, many more galaxies than we thought. Before, 3 years ago I was saying I think there's about 2 trillion galaxies in the universe. That number could be as high as 10 trillion. Big numbers. One of the things you'll notice, I didn't talk about this, but if you look at the James Webb image, you'll see there's a lot of edgy, like kind of thin galaxies. These are, we think, early disk galaxies like the Milky Way. And a few years ago we thought those happened much more recently in time, but it looks like they happened way back in the past. But the real thing, and you hear this all the time in the news, the thing about James Webb that's most surprising is how developed the galaxies are. Why are we seeing these galaxies so soon after the Big Bang? And that is a problem for our models, I'm going to be honest, because our models were based on the old data we had. Nobody expected the universe to form galaxies so efficiently. And so that doesn't mean, by the way, that the Big Bang is wrong, or that you hear this a lot in the news, and I want to emphasize that. It just means our models are wrong, and the models are always wrong at some level. We will figure it out. But why did the universe form these systems so quickly? And this is a big mystery. These show some of the earliest galaxies we've seen with James Webb, these little round blippy things, red dots, so to speak. And there's one idea which is very exotic. I don't know if it's real, but it's certainly something we have to think about. And the idea is that maybe these systems formed so rapidly because you had a lot of dark matter early on. And in this case, although today dark matter doesn't really interact with the stars and such, this could be the collapse of massive amounts of dark matter just producing energy in ways we're not familiar with. So maybe we're seeing dark matter early. The other thing we are seeing early, and this is equally surprising in my mind, are black holes. I mentioned we can see black holes is because they heat up the gas around them. You can see in these images all these bright red kind of dots. Those are in fact young black holes, and we're seeing black holes in the first billion years of the universe. Once again, how did these huge things form? Because some ideas had black holes forming from small black holes, but that takes a lot of time to add them up. So, maybe there's a collapse onto a black hole or something early on. We don't know, but we know they're there, which is really interesting. Okay, so that's what I'm going to say about the universe, but let me just briefly talk about the expanding universe. We'll have a longer talk about this in 2029, with the 100-year anniversary of this result. But there was Hubble's original diagram where he found the expanding universe. And this is the current plot. This is already a little bit outdated, but these are our measurements today going back in time. The Hubble plot is just the first point on this plot. It's just to show that we now can measure the expanding universe out to very large distances. And of course, one of the biggest surprises of the last 20 or 30 years was the fact that it didn't do what we thought it would do. If the universe expanded at a consistent rate, it would follow along that straight line you can see there. You can see on the right kind of the steady model. That's, I think, what most of us believed 30 years ago. The universe was expanding at kind of a steady rate. But in fact, you'll see from the data that in fact it curves upward. And this means that the universe was expanding slower in the past. The universe is accelerating. And this is, of course, a really interesting result that also led to a Nobel Prize. And we believe this is due to this force called dark energy. We don't know much about dark energy. This is the other really big mystery at the moment. There are kind of two main solutions people have for the dark energy. One is that the energy is somehow associated with space itself, and this is called the cosmological constant. And I think this is kind of the preferred model for many physicists. But there's other options. Is the dark energy something we don't really understand, and maybe it changes in time? And I just point out, the data had been looking up until like 3 months ago consistent with the cosmological constant. But there's a new result, you may have seen this, that came out earlier this year from a new experiment called DESI, which suggests that maybe it's not constant. I think it's really early to believe that result, but it'll be interesting to see what happens. And it does matter because the fate of the universe depends on which of these dark energies happen. If the dark energy slows down in time and it reverses potentially, the universe may expand and then come back down on itself in a big crunch. If it's a cosmological constant, it might just keep expanding kind of pleasantly forever. Or if the dark energy increases, it may get to the point where we call the big rip, where the atoms and everything really get stripped apart in a violent way. Good news is none of this is around the corner for you. So once again, something not worth staying up for a night, but it's pretty interesting. And I'll just say again why this, in 1994 when I got my PhD, none of these models were on the table because we didn't even know about the dark energy. That's a really amazing result. There's still another mystery, and you may hear about this quite frequently, and in fact, Chris Burns, who's here, we have our expert, I think he's at the 100 inch today, you can ask him about this. Is that when you measure the expansion rate of the universe locally, it's called the Hubble constant, this is what Hubble first originally measured, there are multiple ways to do it. You could do it using stars, which is kind of the method that Hubble used and people like Wendy Friedman and Chris use, and you get a value for it from that. You can also model the remnant radiation from the Big Bang, which is called the cosmic microwave background. And when you do those two things, you would hope that they would get the same answer, and for a long time they did. But right now they're getting very inconsistent answers for the expansion rate and locally. And so this suggests that maybe there's something else we fully don't understand. Is there new physics here, or are the methods wrong? This is in the news quite frequently too. I'd say this is another big mystery for us to solve, but right now we don't really have the answer. Okay, I'll just end by showing some beautiful futures. Astronomy is driven by telescopes. There's you've seen some remarkable space telescopes. You're going to see some remarkable ground-based telescopes. There's some amazing space telescopes coming. I'm not going to talk about those more. I just thought I would mention the big ground-based telescopes. The European Extremely Large Telescope, built by Europe, EELT, the Giant Magellan Telescope, which is the effort we're leading at Carnegie, that's at our site in Chile, and the 30-meter telescope in Hawaii, all brilliant names that the astronomers have come up with for these things. And the hope is that, these telescopes will be coming online as early as 5-6 years from now, at least some of them. And why are they important? Well, to see the faintest things in the universe, we need bigger and bigger telescopes. I showed you some spectacular James Webb data. James Webb is still a pretty small telescope on modern standards. This is what the Giant Magellan Telescope will look like. These are the 7 mirrors. So the 7 mirrors work together to form a single telescope. And you'll see here James Webb is smaller than one of those mirrors by itself. So these telescopes will really allow us to see the most distant things in the universe. I can't imagine what Edwin Hubble would think today if he could see. Imagine that we're building structures like this. This is a little animation of the Giant Magellan Telescope in Chile. To give you an idea of the scale here, the dome is 22 stories high. That's a 22-story building that rotates. So I just want to point that out in points, and has to withstand a 9.0 earthquakes that we get in Chile. These telescopes are expensive. I'm not going to lie to you. We will not be collecting cash for these telescopes here today, because these are like billion-dollar telescopes. And so right now we're waiting to get investment from the federal government, from the National Science Foundation, to help us complete these telescopes. Because at this level, these are just engineering marvels, but they're going to allow us to answer questions that we don't even yet know. So I'm really looking forward to it. And as I said, hopefully, this one we hope will be online in about 5 or 6 years. So let me end there. I appreciate everybody waiting. I appreciate the heat. I know it's really hard. But let me just say, I just said this. We've come a long way since the century with Edwin Hubble. And no doubt the universe has many more surprises for us. So thank you.